History is not a straight line of progress, but a story of shattering events. Nearly 13,000 years ago, a cataclysm from space may have erased advanced human cultures and forced a complete restart. This is the evidence for a comet impact that reset human civilization. By the end, you will understand how a single cosmic collision links the extinction of mammoths, the birth of agriculture, and ancient flood myths into one revolutionary narrative. How did diamonds smaller than dust become a clue to this global disaster? And why do monuments built by survivors point to the sky in warning? This mystery challenges everything we assume about humanity's past. What does it mean for our own civilization if our greatest leaps forward began with a catastrophe? That dark layer in the soil is a geological crime scene, a moment frozen in time. We call it the Younger Dryas Boundary, a thin, black stripe of sediment that has been identified at dig sites from California to Syria, all dated to around 12,800 years ago. To a geologist, this layer is like a bookmark placed abruptly in the middle of a story, marking a sudden and violent change in the planet's narrative. It was a time when the world, which had been steadily warming after the last ice age, was plunged back into a deep freeze for over 1,000 years. This period is known as the Younger Dryas, a climatic U-turn that reshaped the entire planet. The formation of this boundary layer is the first physical clue that something massive and unnatural occurred. It is rich in charcoal and soot, hinting at continent-spanning wildfires. But the most telling evidence is not what you can see with your eye, but what you need a microscope to find. Scattered within this dark mat are microscopic diamonds, known as nanodiamonds, and tiny, melted glass spheres called microspherules. These materials only form under two conditions: intense industrial pressure or the unbelievable heat and force of a cosmic impact. Their presence here, across continents, points decisively to the sky. Furthermore, this layer shows a dramatic spike in rare elements like platinum and iridium, metals that are vanishingly scarce in the Earth's crust but abundant in asteroids and comets. It is as if the Earth itself collected the forensic evidence from a celestial event, preserving it in this thin, global layer of dust and ash. This boundary marks the precise moment the world turned cold, the very moment great beasts like the mammoth vanished from the Americas and human cultures faced an unimaginable challenge. The ground tells us a catastrophe happened, but to understand its true scale, we must look for the crater it left behind. The search for a crater, a definitive wound in the Earth's crust, proved frustrating for decades. A cosmic event of this magnitude should leave a scar, yet no single massive crater dating to that exact time could be found. This missing piece became a major point of criticism for the impact hypothesis. How could something so devastating leave no obvious hole? The answer may be far more terrifying than a single strike. Instead of one colossal impact, imagine a fragmented comet, a celestial iceberg breaking apart as it screamed into our atmosphere. The result would not be a solitary crater, but a shotgun blast of fire and devastation across an entire continent. This concept of a fragmented airburst, proposed by researchers like Bill Napier, suggests the comet shattered into hundreds of fiery pieces, each exploding in the sky with the force of a nuclear bomb. These atmospheric explosions would have generated unimaginable heat, instantly igniting forests and grasslands across thousands of miles, while sending colossal shockwaves to scour the landscape below. This explains the global layer of soot and the absence of one large crater. The devastation rained down from above. To understand the sheer destructive power of such an event, we must look at a chilling modern analog. In 1908, over a remote Siberian forest, a massive fireball exploded in the sky. the Tunguska event, as it became known, flattened 80 million trees across an area the size of a major city. The explosion is estimated to have been nearly 200 times more powerful than the atomic bomb dropped on Hiroshima, and crucially, it left no crater. The object, thought to be a stony asteroid roughly the size of a 15-story building, disintegrated completely in the atmosphere. Now scale that up. Imagine not one, but dozens of Tunguska-scale events or larger, detonating simultaneously across North America and possibly other parts of the world. The heat pulse would be instant and continental, flash incinerating everything in its path. This model of a fragmented airburst finally provides a mechanism that fits all the clues: the widespread fires, the lack of a traditional crater, and the global rain of microscopic impact debris. It paints a picture of a day when the sky itself turned to fire. But what happened to the world below when that fire fell? From the microscopic evidence, we must now look at a landscape forever changed. Stretching from New Jersey down to Florida, the Atlantic coastal plain holds a secret visible only from above. Scattered across this vast region are hundreds of thousands of shallow, elliptical depressions, often filled with water or vegetation. These are the Carolina Bays, a geological mystery that has puzzled scientists for over a century. From the air, their pattern is unmistakable. They are all oriented in the same northwest to southeast direction, like countless teardrops pointing toward a common horizon. Their shapes are remarkably consistent, with sandy rims raised along their southeastern edges. For a long time, conventional geology explained them as wind-blown or water-formed features from a much earlier era. But their sheer number, their perfect alignment, and their startling uniformity tell a different story to some researchers. Nuclear physicist Richard Firestone and others have proposed a more dramatic origin. They suggest these bays are the scars of secondary impacts created when large, icy fragments of the disintegrating comet struck the Earth's surface or exploded just above it. The force of these impacts or airbursts would have been catastrophic at a local level, liquefying the soil and blasting it outward, carving these oval basins into the soft ground in an instant. The consistent orientation points to a single, incoming direction, as if the entire sky was filled with projectiles arriving from the same point in the northwest. This aligns perfectly with the fragmented comet model, painting a picture of a celestial body breaking apart and showering a continent with destruction. While the debate on their exact origin continues, the Carolina Bays stand as a monumental, if controversial, testament on the landscape. They are potential ground zero markers on a continental scale, visible reminders of a day when the Earth was pummeled from the heavens. But if the land was scarred so profoundly, what happened to the living world that depended on it? The immediate aftermath would have been a cascade of unimaginable hardship. The sky did not just fall that day, it burned. The microscopic diamonds and the strange Carolina Bays point to a cosmic collision, but the most visceral evidence of the catastrophe is written in ash. That dark stripe in the soil, the Younger Dryas Boundary, is more than just dirt. It is a global layer of soot and charcoal. Paleoecologists like Wendy Wolbach have analyzed this layer and found it tells a story of fire on an almost unimaginable scale. This is not the residue of a few scattered campfires or lightning strikes. This is the signature of a planetary firestorm. The hypothesis is as terrifying as it is straightforward. When those fragments of comet exploded in the atmosphere, each detonation would have released a flash of intense thermal radiation, a wave of heat so powerful it could have instantly ignited forests and dry grasslands across entire continents. Picture the heat from a massive airburst combined with a rain of red-hot debris falling from the sky. In a matter of hours, much of North America, and possibly regions of Europe and Asia, could have become a single, roaring inferno. The ecological devastation would have been absolute. Vast habitats were erased in a flash. For the great beasts like mammoths and giant ground sloths, there was simply nowhere to run and nothing left to eat. Their world turned to cinder around them. For the human communities of the time, the Clovis people and others, the fires would have been an apocalyptic event, destroying food sources, sacred sites, and entire ways of life in an instant. But the catastrophe did not end when the flames died down. In fact, the real global crisis was just beginning. Those continent-spanning fires pumped colossal amounts of smoke, soot, and ash high into the atmosphere. This dense, dark cloud would have circled the globe, acting like a shroud over the planet. Sunlight that should have warmed the Earth was instead reflected back into space or absorbed by the particles in the upper air. This is the concept of an impact winter, a sudden, artificial cooling triggered by the debris from a major impact or firestorm. The Earth, which had been gradually warming out of the last ice age, was plunged back into a deep freeze. This is the Younger Dryas period, a climatic U-turn that lasted for over 1,000 years. The world transformed almost overnight from a warming, greening planet into a cold, darkened, and smog-choked landscape. The immediate firestorm was a horror, but the long winter that followed posed an even more profound challenge to survival. How does a civilization, or the scattered threads of many cultures, endure when the very climate turns against them? The world did not simply burn, it froze. In the wake of that fiery cataclysm, a deeper and more enduring crisis took hold. For over 1,000 years, a profound chill settled across the northern hemisphere, a climatic reversal so stark it has its own name, the Younger Dryas. This era is named for a modest Arctic wildflower, Dryas octopetala, whose pollen suddenly dominates ancient sediment layers, a quiet but powerful testament to a world turned cold again. Just as the planet was emerging from the last great ice age, enjoying a warmer, greener phase, something slammed it back into a glacial deep freeze. The impact hypothesis offers a compelling trigger for this dramatic U-turn. The mechanism centers on one of Earth's most vital climate systems, the Great Ocean Conveyor Belt, known formally as the Atlantic Meridional Overturning Circulation. This is a massive, slow-moving current that transports warm, salty water from the tropics northward into the North Atlantic. There, the water cools, becomes denser, sinks, and begins its return journey deep below the surface. This constant churn is a primary heater for Northern Europe and North America. But what happens if you throw a wrench into this delicate machine? Researchers like the pioneering paleoclimatologist Wallace Broecker demonstrated that a sudden influx of freshwater can stall the entire system. Freshwater is less dense than salt water. If a colossal amount of it floods into the North Atlantic, it can form a lid on the ocean's surface, preventing the warm water from sinking. This halts the conveyor belt. Without that northward flow of heat, the continents bordering the Atlantic plunge into cold, and the effects ripple globally. The impact event provides a perfect source for that catastrophic freshwater pulse. Consider the heat generated by those atmospheric explosions over the North American ice sheets, which were still massive at the time. That intense thermal energy could have triggered rapid, catastrophic melting, sending torrents of cold freshwater rushing into the Atlantic Ocean through the St. Lawrence and Mackenzie River systems. In a geological instant, the engine of the ocean's heat pump seized. The result was a climate shock that reshaped the world. Temperatures in some regions may have plummeted by as much as 10 degrees Celsius within a single decade. Growing seasons vanished. Ecosystems that had been thriving for centuries collapsed under the new, harsh regime. This was not a gradual change, it was a violent, planet-wide gear shift. For the magnificent megafauna, from the woolly mammoth to the saber-toothed cat, this abrupt change was a death sentence. Their habitats disintegrated twice over, first by fire and then by ice. For the scattered human populations surviving the initial disaster, the long freeze presented an unrelenting challenge, a bottleneck that would test the very limits of human ingenuity and resilience. The cold snap was a global reset button, but in the silence that followed, a new kind of spark began to flicker. The silence that followed the long freeze was not an empty one. It was marked by profound and sudden absences. Across the continents, the great engines of the Pleistocene world fell still. The woolly mammoth, a creature that had thrived for millions of years, vanished from the Americas. The towering giant ground sloth, the saber-toothed cat, the American camel and horse, all disappeared in a geological blink. This wave of megafauna extinction is one of the most dramatic and poignant clues embedded in the Younger Dryas Boundary. For over a century, the dominant explanations have pointed to human hunters or gradual climate shifts. Yet the timing presents a mystery. These animals had survived countless climate cycles and had coexisted with humans for millennia. Why did so many disparate species, from massive herbivores to formidable predators, all disappear so abruptly right around 12,800 years ago? The evidence on the ground suggests a far more violent and immediate cause. At sites like the Mammoth site in South Dakota, researchers have found something startling. Layers containing mammoth and other megafauna bones are directly capped by that distinctive black mat of sediment. Within that dark layer, and sometimes mixed with the bones themselves, are the same microscopic markers of cosmic violence, the nanodiamonds and melted glass spherules. This is a crucial piece of the puzzle. It tells us these animals did not fade away slowly over centuries. They died in a window of time contemporaneous with the proposed impact event. The mechanism of their passing would have been as multifaceted as the catastrophe itself. The initial firestorms would have incinerated vast grazing lands and forests, removing food and shelter in an instant. For creatures that survived the flames, the ensuing impact winter and rapid climate reversal presented an insurmountable challenge. Their ecosystems, finely tuned to specific conditions, were dismantled twice, first by fire and then by a deep, persistent cold they were not equipped to endure. The loss of these keystone species sent shockwaves through the environment. Mammoths, for example, were ecological engineers, their foraging habits helping to maintain grassland environments. Their disappearance would have triggered a cascade of changes, allowing new types of vegetation to take over and altering habitats for countless smaller species. For the human cultures of the time, this biological collapse was a catastrophe of a different order. These giant animals were not just prey, they were central to survival, providing immense quantities of food, hide, bone, and ivory for tools. A vital resource vanished almost overnight. The world for humanity's ancestors had suddenly become much smaller, poorer, and far more dangerous, with the old ways of life rendered impossible by a scorched and frozen landscape. The question of survival became one of desperate innovation. What new paths did these scattered and resilient communities forge in the ashes of their former world? The story of the great beasts is also a human story, written in stone. Across North America, a sophisticated culture known for its masterful stonework reached its peak just before the darkness fell. This was the Clovis culture, named for the distinctively fluted spear points first discovered in Clovis, New Mexico. These points are works of functional art, carefully chipped to create a central groove that allowed them to be securely hafted to a spear shaft. For centuries, the Clovis people thrived as the continent's premier big game hunters, their technology and settlements spreading far and wide. Their archaeological record is rich and clear until it simply is not. Right at the layer corresponding to 12,800 years ago, the story breaks. The elegant Clovis points vanish from the record. Their campsites are found buried beneath that now familiar black mat of sediment and ash. It is one of archaeology's most abrupt and puzzling disappearances, a cultural collapse that mirrors the biological one happening all around it. For a society so intimately tied to hunting mammoth and other large game, the sudden loss of their primary food source would have been catastrophic. but the challenge was far greater than an empty larder. The very landscape they knew, the migration routes, the water sources, the seasonal camps, all of it was transformed or erased by fire and then locked in a deep freeze. In the face of such total environmental disruption, their way of life became impossible to sustain. The impact hypothesis provides a stark but plausible timeline for this collapse. The event did not give people time to gradually adapt. It presented an immediate existential crisis. Large populations likely fragmented, scattering into smaller, isolated bands in a desperate search for survivable refuges. Some groups may not have made it through the harsh decades that followed, yet human resilience flickered in the darkness. Researchers suggest that the survivors, those who endured the firestorm and the long winter, were forced into a period of incredibly rapid innovation. With the old hunting strategies obsolete, they had to develop new tools for smaller game, for fishing, for processing a wider variety of plant foods. This period of intense adaptation may have been the crucible from which the diverse post-Clovis cultures of the Americas emerged. The disappearance of the Clovis culture is a powerful, human-scale testament to the event's severity. It shows that even an advanced and widespread society was not immune to the forces of a global reset. Their story is a reminder that civilization is not a given, but a fragile thread, vulnerable to the whims of a chaotic cosmos. And if the shockwaves of this event reshaped an entire continent, what echoes did it leave in the collective memory of humanity, passed down across hundreds of generations? Deep within the ice of Greenland, a silent, frozen clock keeps perfect time. Scientists like Paul Mayuski drill deep into the ancient ice sheets, extracting long, cylindrical cores that are nothing less than a layered archive of Earth's past atmosphere. Each annual layer of snowfall, compacted over millennia, traps tiny bubbles of ancient air and a dusting of whatever was floating in the sky that year. It is a pristine record of planetary history, and at the precise depth corresponding to 12,800 years ago, that record shows a startling anomaly. There is a sudden, sharp spike in the concentration of platinum, a metal so rare in Earth's crust that its presence in such abundance can only have one likely source: the dust of a celestial object. This is not an isolated reading. The same platinum signature has been identified in sedimentary layers from a cave in South Africa, from lake beds in Europe, and from archaeological sites in the Middle East. This is the phenomenon of global synchronization. For a geochemical signal to appear simultaneously in ice cores from the Arctic and in dirt from a cave on another continent, the cores must have been truly planetary in scale. A massive volcanic eruption can scatter ash regionally, but it cannot explain a synchronized platinum spike across the entire globe. This pattern of evidence forms a powerful, interlocking case. The microscopic diamonds and glass in the soil of North America, the strange orientation of the Carolina Bays, the soot layer of continental wildfires, and now this global rain of platinum dust, all dated to the same catastrophic moment. Each piece of evidence on its own might be debated, but together they form a coherent and chilling picture of a fragmented comet entering the atmosphere, scattering its remains across the world, igniting the planet, and triggering a climatic chain reaction that lasted for over 1,000 years. The physical evidence is compelling, but it speaks in the language of chemistry and geology. It tells us what happened to the Earth. To understand what happened to humanity, we must listen to a different kind of record, one not written in ice or stone, but carried on the breath of survivors across hundreds of generations. These ice cores and soil layers hold the physical truth of the event, but humanity carries its own record. Around the world, in cultures separated by vast oceans and millennia, the same terrifying story is told. It is a story of fire from the sky, of a great flood that swallowed the land, and of a darkness or a cold that lasted for generations. These are not coincidences of imagination. They are the echoes of a shared trauma, passed down from those who witnessed the cataclysm and survived to tell of it. Consider the ancient Greek myth of Phaethon, a young man who pleaded to drive the chariot of the sun for a single day. Losing control, he plunged too close to the earth, scorching the continents, drying up rivers, and blackening the skin of entire peoples before being struck down by Zeus. The story reads like a poetic description of a massive atmospheric fireball and its aftermath. Across the Atlantic, numerous Native American traditions speak of a time when the sky fell, or when a great serpent of fire descended, bringing devastation. The Luiseno people of California tell of a flood of pitch that covered the world, a possible memory of raining, burning tar from ignited oil fields. And then there are the flood myths, so universal they form a cornerstone of human storytelling. From the Mesopotamian epic of Gilgamesh to the biblical story of Noah to legends from the Amazon and Australia, the narrative is consistent, a deluge sent by higher powers to cleanse a world, with only a warned few surviving. Science offers a potential trigger for these memories. The impact of a fragmented comet into the North American ice sheet could have generated colossal tsunamis that raced across continents. The sudden melting and the climatic chaos would have disrupted ocean currents and caused rapid, dramatic changes in sea levels, perhaps explaining stories of lands disappearing beneath the waves. Scholars who study this intersection, like anthropologist Bruce Mass, analyze these myths not as literal histories, but as encoded events. They look for common details, the direction from which the danger came, the nature of the destruction, and the environmental changes described. When these details are mapped, they often converge on a time frame and a type of event that aligns strikingly with the Younger Dryas Boundary evidence. These stories are humanity's first attempt at disaster science, a way to process a world-altering event through the language of gods and heroes. They give a voice to the silent geological data, adding the human dimension of fear, loss, and ultimate resilience. They remind us that our oldest stories may be memories fossilized in tradition. This bridge between myth and physical evidence is profound, yet it begs a more concrete question. If the sky truly fell in a rain of fire, where did the largest piece strike? Is there a crater, a ground zero, that we have overlooked? The missing crater was the theory's greatest weakness, a ghost at the scene of the crime. For decades, skeptics could rightly ask, where is the wound? If a cosmic impact reset the world, surely it left a hole. Then, in 2018, a team of scientists peered beneath the ice of northwest Greenland and found it. Using advanced radar technology from aircraft, they mapped the contours of the land hidden under nearly a kilometer of ice. What they revealed was staggering, a perfectly circular depression measuring 31 kilometers across, nearly the size of the city of Paris. This is the Hiawatha crater, a colossal impact structure that had remained a secret for millennia, preserved under the frozen expanse of the Hiawatha Glacier. The discovery, published in the journal Science Advances by a team led by researcher Kurt Kjær, sent shockwaves through the scientific community. Here, at last, was a candidate for a primary impact site, a ground zero with a date that fit perfectly within the Younger Dryas timeframe. The crater's morphology told a violent story. Its raised rim and central peaks are classic signatures of a high-velocity impact from a massive, iron-rich object. This was not a gentle touchdown, it was a collision of apocalyptic force. Researchers even found grains of shocked quartz in sediments washed out from under the glacier, a mineral that forms only under the extreme pressures of a cosmic impact. The energy released would have been beyond human comprehension, equivalent to millions of the most powerful nuclear weapons ever built detonating at once. While precisely dating a crater buried under ice is a monumental challenge, the evidence strongly suggests it formed very recently in geological terms, quite possibly within the last 100,000 years. The Hiawatha crater transforms the narrative. It moves the discussion from a fragmented airburst with no central point to a scenario that includes a direct colossal strike. An iron asteroid of that size could have been the largest fragment of that disintegrating comet, the parent body whose breakup spawned the swarm of smaller pieces that rained fire across the continent. Its location in the northwest also provides a compelling explanation for the uniform orientation of the Carolina Bays, as if all those elliptical scars were pointing back toward the origin of the incoming swarm. This silent witness under the ice is a game-changer, a monumental piece of physical evidence that answers the critics' most persistent question. It gives the catastrophe an epicenter. But if such an impact occurred, what did it do to the very fabric of the planet in that immediate, terrifying moment? The numbers behind the Hiawatha impact are almost impossible to grasp. To translate that silent crater under the ice into a real-world event, scientists must calculate the violence. The estimates are staggering. If the object that struck Greenland was a dense, iron-rich asteroid fragment, perhaps 2 kilometers wide, the energy released upon impact would have been equivalent to over 100 million megatons of TNT. To put that in human terms, that is millions of times more powerful than the atomic bomb dropped on Hiroshima. This single event would have unleashed more destructive force than all the explosives used in every war in human history combined, and then multiplied many times over. The energy would not have been contained at ground zero. It would have radiated outward in 3 devastating waves. First, a thermal pulse of unimaginable heat, flash igniting everything combustible for hundreds of kilometers. Second, a supersonic shockwave that would have scoured the landscape, flattening forests and generating winds stronger than any hurricane. Third, if the impact struck the ice sheet or the ocean, colossal tsunamis would have raced across the Atlantic, inundating coastlines with walls of water hundreds of meters high. Computer models simulating such an impact show its effects would not be regional but hemispheric, with debris and climatic shockwaves engulfing the planet. But what if the primary devastation came not from a single ground strike, but from a swarm of atmospheric explosions, like the Tunguska event but magnified 1,000-fold and scattered across a continent? The total energy released could still reach those same cataclysmic scales. The math confirms that either scenario, a direct hit or a fragmented airburst barrage, possesses more than enough power to explain the global forensic evidence, the continent of fire, the rapid climate reversal, and the abrupt biological collapse. This mathematical modeling is crucial. It transforms the hypothesis from a compelling story into a physically plausible, quantified scenario. It demonstrates the precise mechanism of a civilization reset, a shock so profound it could erase one way of life and force the desperate invention of another. In the long, cold shadow of such an event, where would you even begin to rebuild? The long winter did not last forever. Slowly, the world began to thaw again, but the landscape that emerged was irrevocably changed. Scattered bands of survivors faced a new reality, a harsher, colder world where the old hunting grounds were gone, and the great beasts were now just memories etched in story. In this stark environment, humanity's journey took a decisive and revolutionary turn. We call it the Neolithic Revolution, the dawn of agriculture and settled life. For generations, the story has been one of slow, inevitable progress, a clever discovery in a land of plenty. But what if the truth is far more dramatic? The impact hypothesis offers a compelling reframe. Agriculture was not an invention of abundance, but a desperate adaptation born from catastrophe. The traditional timeline is itself a clue. The Younger Dryas cold snap ended around 11,600 years ago. Almost immediately afterward, in the region known as the Fertile Crescent, the first evidence of plant domestication appears. This is not a slow, 1,000-year drift toward farming. It is a rapid pivot following a global reset. With the megafauna vanished and climates still unpredictable, the old nomadic lifestyle of following herds became untenable. Human communities were backed into a corner, forced to innovate or face hardship. They began to intensively manage the plants and animals that had survived around them, protecting favored grasses, selectively sowing seeds, and corralling wild goats and sheep. This was not a leisurely experiment, it was a survival strategy. Domestication, in this light, looks less like a brilliant idea and more like a necessary response to a world suddenly emptied of its primary food sources. This perspective reshapes our entire understanding of civilization's origins. Archaeologists like George Dodwell have pointed to ancient monuments and calendars, suggesting they show a profound recognition of a changed world, an attempt to reorder time and space in the wake of cosmic chaos. The drive to settle, to build granaries, to coordinate planting, these needs accelerated social complexity at a breathtaking pace. Leadership, hierarchy, and specialized roles became essential for managing shared resources and labor. The Comet impact, therefore, may have been the painful, violent catalyst that spurred humanity off the hunter-gatherer path and onto the accelerated road toward cities, writing, and empires. It connects a cosmic event directly to the foundation of our modern world, suggesting that our greatest leap forward began not in a moment of peace and plenty, but in the resilient aftermath of a global disaster. This raises a profound and unsettling question. If our civilization was born from the ashes of a cataclysm, what does that mean for the monuments our ancestors built, not just as homes, but as warnings? The comet that may have reshaped our past is not a solitary ghost. It left a family behind, a celestial river of debris still crossing Earth's path. This is the Taurid meteor stream, a vast and dusty trail associated with a comet named Encke. Some researchers, including astronomer Bill Napier, propose a startling idea. They suggest Comet Encke is merely a large fragment of a much greater comet that broke apart thousands of years ago, the very parent body of the Younger Dryas event. This means the Taurid stream could be the lingering debris field from that ancient catastrophe, a cosmic crime scene we pass through twice every year. Most encounters are harmless, producing the beautiful Taurid meteor showers we see in late autumn. But this stream is not just dust. Radar and telescopic surveys have revealed it also contains a population of larger objects, some hundreds of meters across, hidden within the cloud of smaller particles. Earth's orbit periodically takes us through denser knots within this stream, periods that may last for decades or even centuries. During these hazardous windows, the statistical risk of a significant impact increases. The Tunguska event of 1908, that immense airburst over Siberia, is considered by many astronomers to be a likely candidate, a small fragment from the Taurid complex reminding us of its latent power. This connection transforms the story from ancient history into a pressing, cyclical reality. By studying the geological forensics of the Younger Dryas, we are not just piecing together a past disaster, we are calibrating a warning system. We learn about the frequency of such events, the nature of the objects involved, and the devastating cascades they can trigger. It reminds us that humanity's journey on this planet occurs within a dynamic and sometimes dangerous solar system. Our survival and progress are not guaranteed, but are interwoven with an ongoing cosmic dialogue. To fully hear that dialogue, to read the evidence left behind, we must employ the most precise tools science has ever devised. The whispers in the soil and ice are faint, requiring ears of silicon and steel to hear them clearly. To unravel a catastrophe 12 millennia old, science has built its own kind of time machine, a suite of technologies that peer into the molecular fabric of the past. At the heart of this detective work is a machine with a name as powerful as its function, the Accelerator Mass Spectrometer. This device does not simply estimate age, it counts individual atoms. By measuring the precise decay of rare carbon-14 isotopes in a single speck of charcoal from that black boundary layer, scientists can date the moment of burning to within a handful of decades, an astonishing feat of precision for an event so ancient. But what burned? For that, researchers turned to another formidable tool, the scanning electron microscope. Under its incredible magnification, a mundane grain of dust becomes a landscape. It is here that the true identity of those nanodiamonds is confirmed. Their distinct crystalline lattice, a unique fingerprint of formation under the extreme pressure of a cosmic impact. This is forensic science on a planetary scale. The search for extraterrestrial evidence extends to the realm of the vanishingly small. Techniques for platinum group element analysis can now detect traces of metals like iridium and platinum at concentrations of a few parts per trillion, akin to finding a single unique grain of sand on an entire beach. It is this sensitivity that allowed scientists to identify that synchronized global spike in platinum, the chemical signature of a comet's dust settling across the world. Meanwhile, from the sky itself, another technology maps scars invisible from the ground. LiDAR, which stands for light detection and ranging, uses laser pulses to strip away modern vegetation, revealing the bare topography beneath. It is through LiDAR surveys that the staggering number and perfect alignment of the Carolina Bays became undeniably clear, transforming them from curious ponds into a continent-wide pattern demanding explanation. Each technological leap peels back another layer of time, providing higher resolution data to test the hypothesis. This is not the work of a single field, but a convergence, geology providing the samples, physics and chemistry analyzing them, and remote sensing mapping the context. It is a multidisciplinary toolkit that exemplifies how modern science interrogates the deep past, turning whispers from the sediment into a shouted, data-driven narrative. With these powerful tools now focused on the mystery, we can ask a more intimate question. What did this global reset feel like for the people who lived through it, and what unmistakable marks did it leave on their behavior and their very bones? The most profound questions are often carved in stone. Rising from a barren hilltop in southeastern Turkey, Göbekli Tepe stands as one of archaeology's greatest and most beautiful mysteries. This is not a city or a fortress, but a series of circular enclosures built from massive, T-shaped limestone pillars, some weighing over 10 tons. They are arranged with clear intention and decorated with breathtakingly intricate reliefs of animals, foxes, snakes, birds, and scorpions, all rendered with an artistic skill that feels utterly timeless. The date of its construction is what sends a shockwave through our understanding of history. Göbekli Tepe was built around 11,500 years ago. That places its creation immediately after the Younger Dryas cold snap ended, in the very dawn of the new climatic era. According to traditional models, the people of this time were simple hunter-gatherers, nomadic bands focused solely on day-to-day survival. They should not have had the surplus labor, the specialized skills, or the complex social organization required to quarry, transport, and erect monuments of this scale and sophistication. This site predates the invention of pottery, the wheel, and even settled agriculture by thousands of years. It is an architectural anomaly that seems to have arrived fully formed, a masterpiece out of its proper time. Mainstream archaeology interprets Göbekli Tepe as a ritual center, a sacred meeting place for scattered groups, which is a compelling explanation for its purpose. But its timing whispers a more dramatic possibility to some researchers. Could this be more than a temple? Could it be a response, a cultural scar tissue formed after a global trauma? Think of the context. If the generations before had witnessed a sky of fire and endured a 1,000-year winter, the very heavens would have become a source of terror and awe. Building a monumental site aligned to the stars could have been an act of desperate meaning-making, an attempt to understand, placate, or track the cosmic forces that had so recently shattered their world. The elaborate animal carvings might not just be totems, but a preservation of knowledge, a catalogue of species that survived, or a warning of dangerous powers. The sheer effort required to build it speaks of a society with a powerful, unified drive, perhaps forged in the shared memory of a cataclysm. This is where figures like Graham Hancock introduce a provocative idea. They suggest Göbekli Tepe might not represent the beginning of something new, but the lingering echo of something much older. Could it be a survivor colony, built by people who carried forward fragments of knowledge from a more advanced pre-impact culture, a culture largely erased by the comet and the ice? While this remains a speculative fringe theory, it forces a vital re-evaluation. Göbekli Tepe proves that the humans emerging from the Younger Dryas were capable of far more than we ever imagined. They were not primitive survivors scraping by. They were architects, artists, and astronomers who felt a profound need to build something permanent and meaningful against the backdrop of a recently chaotic cosmos. The site is less a question about their capabilities and more a question about their motivation. What urgent message, or what deep memory, compelled them to raise these stones with such incredible effort at the very dawn of a new age? The stones of Göbekli Tepe speak of memory and sky, but the soil itself holds a more elemental truth. To understand the true nature of the cataclysm, we must read the language of the cosmos written in atoms. The Earth's crust is a chemical diary, and at the Younger Dryas Boundary, the entries are written in elements from the stars. Think of our planet being gently, catastrophically, dusted with a thin layer of cosmic material, a telltale residue left by an extraterrestrial visitor. The most famous of these celestial fingerprints is iridium. This silvery white metal is incredibly rare on the Earth's surface, but it is abundant in asteroids, comets, and meteorites. Its discovery in a global layer was the key piece of evidence that convinced the world a massive asteroid impact ended the age of dinosaurs. That same telltale sign appears at the Younger Dryas Boundary, alongside a sharp spike in platinum, another element with a pronounced cosmic heritage. Finding these metals in such concentration, in a layer dated to the same moment across the globe, is like finding gunpowder residue at a crime scene. It points directly to a source beyond our world, but the cosmic chemistry goes deeper into the realm of the truly exotic. Within that dark layer, scientists made an even more startling discovery: molecules shaped like microscopic soccer balls. These are fullerenes, often called buckyballs, cage-like structures of carbon atoms that can form in the intense conditions of deep space. A team of researchers, including geochemist Luan Becker, identified these fullerenes in sediments from the Younger Dryas Boundary. The molecules themselves were fascinating, but what they carried inside was revolutionary. Trapped within those carbon cages were specific isotopes of helium, gases with a distinct atomic signature that does not match anything native to Earth or even our solar system. This helium had an extraterrestrial origin, likely from the interstellar medium. It was a smoking gun within a smoking gun. The fullerenes acted as tiny, indestructible capsules, preserving a sample of the impacting object's very essence as it vaporized in our atmosphere. This chemical evidence provides a forensic fingerprint of astonishing specificity. It does not just suggest an impact, it suggests the impactor had a distinct chemical composition, possibly that of a comet from the outer reaches of the solar system or even interstellar space. This cosmic dusting of iridium, platinum, and interstellar fullerenes forms one of the most robust and technically compelling lines of evidence. A story told not in myths or monuments, but in the immutable language of atomic bonds and isotopic ratios. Yet, as with any paradigm-shifting idea, this chemical narrative has been met with intense scrutiny and alternative explanations. The strength of a theory is not measured by its evidence alone, but by how well it withstands the fires of scientific debate. A scientific revolution rarely begins with a quiet consensus. The proposal that a comet impact reset human civilization ignited one of the most passionate and productive debates in modern Earth science. Picture a conference hall where the air hums not just with ideas, but with genuine intellectual friction. On one side, researchers present maps of platinum spikes and images of microscopic diamonds. On the other, respected voices from geology and archaeology raise pointed, necessary questions. This is not a sign of a weak theory, but of a healthy one, a hypothesis being tested in the crucible of peer review. Skeptics have played a vital role, challenging every assumption and forcing a refinement of the evidence. A key objection centers on the microspherules and nanodiamonds themselves. Could these tiny markers have a more mundane origin? Volcanologists note that intense wildfires can create glassy spherules, though not typically in the abundance or specific forms found at the boundary. Cosmic dust, a constant rain of microscopic material from space, accumulates slowly over millennia. Could the Younger Dryas layer simply represent a concentrated patch of this normal dust? These are valid questions that demand clear answers. Proponents responded by refining their search, identifying specific types of nanodiamonds, like lonstellate, that form almost exclusively under the extreme shock pressure of an impact, not in a forest fire. They began collecting samples with even more rigorous contamination controls, showing the layer is a sudden event, not a gradual accumulation. Another major point of debate involves timing. Is the evidence truly synchronous across the globe? Could the black mats in North America, the platinum in Greenland ice, and the cultural shifts in the Middle East all be neatly tied to the same decade? Or are we seeing a mosaic of different events smeared across centuries? Critics rightly point out the challenges of precise dating across such vast distances and different materials. This skepticism has driven incredible improvements in methodology. The use of accelerator mass spectrometry has become more widespread, allowing for dating with razor-thin margins of error. Researchers now seek multiple lines of dating at a single site, cross-referencing carbon dates with layers of volcanic ash or annual ice layers to build an irrefutable chronological case. The result of this intense scrutiny is that the hypothesis has evolved. It has moved from the fringe of speculation to the pages of serious, peer-reviewed journals like Science and Proceedings of the National Academy of Sciences. It is no longer dismissed out of hand, but engaged with as a legitimate, though not yet proven, scenario. This journey through controversy is the engine of science. Each critique forces a stronger defense, a better experiment, a clearer map. The theory, like the world it describes, is being tempered by fire. And if this cosmic event is so deeply woven into our past, could it also hold a mirror to our psychological present, revealing how humanity processes existential fear across the ages? The strength of this idea lies not in a single clue, but in the convergence of many. This is not a story told by one science, but a chorus of voices from across the entire spectrum of human knowledge. Imagine a vast intellectual puzzle where a climatologist's ice core, showing a sudden platinum spike, fits perfectly with an archaeologist's discovery of a cultural layer buried under black ash. That layer, in turn, aligns with a geologist's identification of microscopic diamonds in the soil and an astronomer's model of a fragmented comet crossing Earth's orbit. Each piece comes from a different field, speaking its own technical language, yet they all point to the same moment in time. This interdisciplinary synthesis is the true power of the hypothesis. It is the hallmark of the work done by groups like the Comet Research Group, which brings together geologists, paleontologists, nuclear chemists, astronomers, and even experts in ancient texts. They are not looking for evidence to fit a pre-written story. They are allowing the evidence from a dozen independent fields to write the story together. When a geochemical signal from Greenland matches a paleontological extinction event in Arizona, which coincides with an archaeological collapse in Ohio and is echoed in flood myths from Mesopotamia, we move beyond coincidence. This creates a web of support where each strand strengthens the others. A climatologist might not recognize a carved pillar as evidence, and an archaeologist might not understand the significance of a helium isotope, but when their findings are placed side by side, a profound pattern emerges. This approach models how we should investigate our deepest historical mysteries by breaking down the walls between academic silos. It acknowledges that the past does not respect our modern categories of study. To understand a planet-altering event, we must think in connected, systemic ways, seeing the Earth as a single, interconnected organism that records trauma in its ice, its soil, its fossils, and even in the stories of its inhabitants. This synthesis paints a compelling picture of catastrophe and renewal. But to fully grasp the scale of what was lost, we must first ask, what was the world like on the eve of destruction, just before the sky fell? To truly feel the magnitude of what was lost, we must first attempt to see the world that existed in the calm before the cosmic storm. The evening of 12,800 years ago was not a blank page. Human communities were not simply waiting in primitive silence for history to begin. They were living within rich, complex cultures that have left only the faintest whispers in the stone. We have no evidence for a globe-spanning industrial civilization, no ancient cities of steel, but to assume they had nothing to lose is to underestimate the human spirit entirely. Imagine a tapestry woven not from durable threads of stone, but from fragile materials like spoken word, woven fiber, carved wood, and carefully tended knowledge. This is the lost world we must try to reconstruct. What might have filled that tapestry? We can look at the capabilities demonstrated at places like Göbekli Tepe, built just after the crisis, and reason backwards. The organizational skill to build it did not emerge from a vacuum. It suggests pre-existing social structures capable of coordinating large groups, perhaps for seasonal gatherings, trade fairs, or spiritual ceremonies that wove different bands together. Widespread trade networks are a strong possibility. A distinctive type of stone tool or a rare shell found hundreds of miles from its source is a clue to a web of connection and exchange, a web that would have snapped under the strain of continent-wide fire and ice. Their knowledge of the world was likely profound, carried in memory and song. Oral histories could have preserved genealogies and events across hundreds of generations. Astronomical knowledge, crucial for navigation and timing seasonal migrations, might have been far more sophisticated than we credit, encoded in stories about the stars that were lost when the storytellers fell silent. We might even consider proto-agricultural practices, not full-scale farming, but the deliberate tending of favored wild plants, a symbiotic relationship with the landscape that left no permanent fields or seeds in the archaeological record. Then the comet struck. Think of the impact not as an eraser that wiped the slate completely clean, but as a filter. It selectively destroyed the most fragile and beautiful parts of that cultural tapestry. The vast trade networks collapsed as routes became impassable and trading partners vanished. The intricate oral histories, those libraries of memory held in the minds of elders, were tragically vulnerable as entire communities were displaced or lost. Perishable technologies, things made of leather, wood, or fiber, rotted away without a trace. Social hierarchies and alliances, maintained through generations of ritual and reciprocity, shattered under the pressure of sheer survival. What remained? The durable, the stubborn, the simple, stone tools, hearths, the deepest layers of instinct and grit. This filtering effect creates a profound distortion in the archaeological record. We are left sifting through the rubble of a civilization's basement, while the upper floors, where the art, the music, the lore, and the poetry resided, were vaporized. This challenges our most comforting assumption about human history, the idea of linear, constant progress from simple to complex. Instead, we are confronted with a more cyclical story, one of cultural peaks, catastrophic collapses, and resilient rebirths from a handful of seeds. This speculative glimpse does not require lost cities or advanced machinery to be deeply tragic and equally inspiring. It suggests that before the reset, humanity had already woven a world rich with meaning, connection, and knowledge. The impact did not just kill the mammoths and chill the planet, it severed a million threads of cultural memory. And yet, from the survivors who carried those few durable fragments forward, the entire, magnificent tapestry of our world was slowly, painstakingly rewoven. This realization frames their resilience not just as a fight for physical survival, but as a courageous act of cultural recreation. It makes the monuments they built afterward not just temples, but perhaps tombstones and declarations of hope combined. The story of the survivors is written in their bones and in the very code of life they passed forward. While stone tools can shatter and oral histories can fade, our genes carry a deeper, more ancient memory. Scientists studying human genetics have uncovered a pattern that echoes the archaeological silence, a series of dramatic population bottlenecks scattered across our ancestral timeline. A genetic bottleneck is not a physical object, but a statistical shadow. It occurs when a population shrinks so severely that only a small fraction of its original genetic diversity survives to be passed on to future generations. It is like taking a vast library of unique books and preserving only a single, randomly chosen shelf. The rest of the stories are lost forever. Researchers analyzing the DNA of modern populations can detect these events by measuring the reduction in genetic variation. They look for points in time when it appears that all living humans descended from a remarkably small number of founding ancestors. Several such bottlenecks have been identified, and while pinning them to an exact calendar year is challenging with current technology, one of the most significant appears to cluster in the general time frame following the Younger Dryas Boundary. This is not a coincidence, it is a biological echo of the catastrophe. Imagine those scattered bands of humans, the ones who endured the firestorms and the long winter. Their world had become a series of isolated refugia, pockets of marginally survivable land separated by vast, scorched or frozen barriers. Groups that might have numbered in the hundreds were reduced to mere handfuls. In such extreme conditions, survival was a brutal lottery. A single failed hunt, an outbreak of illness, or a harsh winter could mean the end of an entire lineage. The genetic diversity that had built up over millennia in different populations was suddenly and violently pruned. The survivors who eventually repopulated the continents did so carrying only a subset of humanity's original genetic library. This is why, from a genetic standpoint, all humans today are remarkably similar. We are the children of those few resilient lines that made it through the bottleneck. This biological evidence provides a silent, powerful corroboration of the archaeological record. The disappearance of specific tool-making traditions and the cultural disruption seen in the layers of soil find their parallel in the narrowing of the human family tree. It tells us the event was not just an environmental or cultural reset, but a demographic one, a brush with a form of extinction that left an indelible mark on who we are. Every person alive today carries within their cells a legacy of that ancient winter, a testament to the fragility and the fierce tenacity of our species. This shared, near-universal experience of loss and survival on a planetary scale must have left a profound psychological imprint. How did these early communities, bearing this genetic and cultural trauma, begin to make sense of a world that had so recently tried to erase them? The trauma of the sky falling would have rewritten humanity's relationship with the cosmos itself. For generations after the cataclysm, the heavens were no longer just a beautiful tapestry of stars, they were a source of profound mystery and potential danger. This shift in perception may have ignited the very spark of cosmic religion, the first spiritual leaders, the shamans and storytellers of those recovering communities, faced a fundamental question. How do you explain a force so vast and destructive it could reshape the entire world? The answer likely took shape in the stars. The gods themselves may have migrated skyward, becoming associated with the sun, the moon, and the wandering points of light that were the planets. A comet or a meteor shower was no longer just a light show. It could be seen as a deity expressing anger or a portent of another great change. This was not mere superstition. It was a form of early disaster science, an attempt to find patterns in the chaos to ensure survival. The development of systematic astronomy and its companion practice of astrology may have deep roots in this collective trauma. Watching the sky became a sacred duty, a way to seek warnings. If you could predict the regular motions of the sun and moon, you could perhaps identify when something irregular and threatening entered the picture. This drive to find order in the celestial realm gave rise to some of humanity's most enduring monuments. Consider the great stone circles like Stonehenge in England or the elaborate solar observatories of ancient Egypt. These are often interpreted as calendars or temples, which they certainly were, but viewed through the lens of a cosmic catastrophe, they take on another layer of meaning. They could be seen as early warning systems, stone computers built to track the cycles of the sky with meticulous precision, born from a cultural memory that the greatest danger comes from above. The alignment of these structures with solstices and equinoxes was not just about marking seasons for planting, but about maintaining a constant, vigilant dialogue with the cosmos, ensuring the sun would return and no unexpected visitor would arrive unseen. This perspective weaves together our oldest spiritual and scientific impulses, the human desire to connect with the divine and the drive to observe, measure, and predict the natural world may have been forged in the same fiery event. It suggests that our awe of the stars is intertwined with an ancient, inherited caution. The legacy of that day is not just in our genes or our tools, but in our very urge to look up and search for meaning in the infinite dark. This leads us to a pivotal moment in the modern era, when a handful of researchers looked at the scattered pieces of this ancient puzzle and dared to ask a question that would redefine our past. The Tunguska event was a whisper compared to the Younger Dryas roar, but its echo is invaluable. In the early morning of June 30th, 1908, a blinding fireball streaked across the Siberian sky and exploded with the force of a modern thermonuclear weapon. The Airburst, estimated at 5 to 10 miles above the ground, released energy hundreds of times greater than the Hiroshima bomb. It flattened 80 million trees across an area over 2,000 square kilometers, radiating outward from the epicenter in a pattern of devastation that looked like a giant butterfly stamped upon the earth. When expeditions finally reached the remote site years later, they found no crater. The object, likely a stony asteroid roughly 60 meters wide, had vaporized completely in the atmosphere. This single event provides the clearest modern blueprint for an airburst catastrophe, a demonstration of how immense energy can be delivered from the sky without a single impact scar on the ground. The Tunguska event was a solitary warning shot. More than a century later, a much smaller but more public reminder arrived. On February 15, 2013, a brilliant meteor blazed across the morning sky over the Russian city of Chelyabinsk. This object, about 20 meters across, exploded at an altitude of nearly 20 miles. The flash was brighter than the sun, visible for hundreds of kilometers. But the real damage came from the shockwave that followed minutes later. Traveling at the speed of sound, it shattered windows across the city, sending glass flying and injuring over 1,000 people, mostly from cuts and bruises. Security cameras captured the surreal moment, making the cosmic threat viscerally real for a global audience. The Chelyabinsk meteor was a tiny fragment compared to Tunguska, yet its shockwave damaged thousands of buildings and served as a stark lesson in secondary effects. These two events, separated by a century, are not relics of a violent past. They are data points in an ongoing process. For scientists modeling the Younger Dryas catastrophe, they are crucial scaling tools. Tunguska shows the destructive footprint of a roughly 60-meter object. To create the continent-wide effects proposed for the Younger Dryas, researchers scale this model upward, envisioning a swarm of fragments, each potentially much larger than the Tunguska object, detonating in a coordinated aerial barrage across North America. The physics remains the same, only the magnitude changes exponentially. These analogs help us comprehend the mechanics, the sudden flash of heat that ignites everything below, the supersonic blast wave that scours the landscape, and the rain of shattered, superheated debris. They transform an abstract ancient catastrophe into a physically plausible, modeled event. More importantly, they shatter the comforting illusion that such things only happened long ago. Tunguska and Chelyabinsk remind us that Earth orbits within a cosmic shooting gallery, and our atmosphere provides only a partial shield. The objects that cross our path are part of a continuum, from the dust that creates shooting stars to the mountain-sized asteroids that shaped planetary history. Studying these modern events is not just about understanding the past, it is about calibrating our future vigilance. They give urgency to the search for near-Earth objects and lend sobering credibility to the idea that our ancestors' greatest trial may have literally fallen from the sky. If such events are woven into the fabric of our planetary life, then the question becomes not if, but when the next significant encounter will occur. And that shifts our gaze from ancient forensic geology to a very modern and practical endeavor, the science of planetary defense. These modern encounters provide a scale, but to reconstruct an ancient cataclysm we need a different kind of tool. In the absence of a time machine, the most powerful instrument we possess is not a telescope or a drill, but a supercomputer. This is where raw data transforms into a living, virtual world, where scientists can stage the disaster again and again to see if the story holds together. Teams at places like Los Alamos National Laboratory feed every known variable into immense simulations. They program in the likely trajectory of a fragmented comet, the physics of its screaming entry into the atmosphere, and the complex equations governing our planet's climate systems. With a push of a button, they can watch a digital version of history unfold. These are not simple animations, they are rigorous computational experiments that obey the unbreakable laws of physics. Researchers can adjust key parameters, asking what happens if the fragments are primarily icy or stony, if they arrive at a shallow angle or steeply, if they explode at a high altitude or lower in the atmosphere. They run the simulation thousands of times, each with a slight variation, searching for the scenario whose aftermath most closely mirrors the evidence we dig from the ground. The results are illuminating. The models show that a swarm of airbursts, each with the energy of a large nuclear weapon, could indeed generate a thermal pulse intense enough to ignite wildfires across a continent. They demonstrate how the sudden injection of heat and soot into the upper atmosphere could alter wind patterns and block sunlight, triggering a rapid cooling. Crucially, they can simulate the effect of that heat on the North American ice sheets, calculating the volume of meltwater that would surge into the Atlantic Ocean and showing how that freshwater lid could stall the Great Ocean Conveyor Belt, plunging the Northern Hemisphere into a deep freeze for centuries. This virtual experimentation is the critical bridge between correlation and causation. Finding platinum in the ice and charcoal in the soil shows these events happened at the same time, but it does not prove one caused the other. The computer models provide the mechanistic link, the step-by-step physical explanation for how a cosmic event in the sky could lead to frozen ground in Europe and extinctions in America. They turn a collection of fascinating clues into a testable, physical narrative. By finding the digital scenario that best matches the geological crime scene, scientists move from wondering if it could have happened to understanding precisely how it might have happened. This computational power allows us to run the experiment we can never perform in reality, offering a glimpse into one of Earth's most pivotal days. Yet even the most elegant simulation must ultimately be judged against the hardest evidence of all, the unyielding truth written in stone and bone. A definitive conclusion remains just out of reach, held within a handful of stubborn, unanswered questions. The scientific process thrives on these open ends, and they are now the very engines driving new research. Take the Hiawatha crater, that colossal scar beneath the Greenland ice. While its discovery was monumental, its exact age is still a subject of intense focus. Scientists are working to extract and analyze mineral grains from beneath the glacier, searching for definitive isotopic signatures that will lock its formation date to that pivotal moment 12,800 years ago. This precise dating is a holy grail, a potential linchpin that could solidify the entire timeline. Elsewhere, eyes are turning to other remote frontiers. If one crater lay hidden under ice for millennia, could others be concealed under ocean sediments or beneath the remaining ice sheets of Antarctica? The search continues, using sophisticated sonar and radar mapping to scan these uncharted regions for more hidden wounds from that ancient barrage. Another major puzzle involves the climatic data itself. Records from the southern hemisphere show a less dramatic temperature plunge during the Younger Dryas period. Why would a global event show such a pronounced northern bias? Researchers are modeling atmospheric circulation patterns and ocean currents to understand how the heat distribution and soot from fires might have been concentrated in the north, creating a more severe regional effect while the southern continents experienced a more muted change. This asymmetry is not a refutation, but a complexity that demands a more nuanced global model. Then there is the celestial detective work, the search for the parent body. Is Comet truly a remnant of that larger object? Astronomers are meticulously tracking the orbits and compositions of objects within the torrid stream, looking for chemical family resemblances that could tie them back to a single, shattered source. Some researchers even explore the possibility of multiple closely timed events, a series of impacts over a few centuries rather than a single catastrophic day, which could explain certain layers in the geological record. Every new archaeological dig that uncovers a settlement layer directly beneath the black mat, every ice core that reveals another geochemical spike, adds another data point. This is not a settled story gathering dust in a textbook. It is a vibrant, active mystery with papers published regularly that refine, challenge, and expand the hypothesis. This dynamic state of inquiry is what makes science so compelling. Our understanding of this profound chapter in human prehistory is still being written, and the next discovery, perhaps from a drill core or a satellite scan, could be the one that turns a compelling theory into an established fact. The journey is far from over, and that is the most exciting part of all. The story of the comet is ultimately a story about us. It forces a humbling reflection on the dual nature of our existence, a civilization capable of both breathtaking resilience and heartbreaking fragility. Look at the survivors of that ancient winter, those scattered bands clinging to life in a world turned to ash and ice. They possessed no advanced technology, no global network to call upon for aid. Everything they had known was gone, yet from that absolute zero they began again. Over generations, through trial and error passed down by word of mouth, they rediscovered how to thrive. They domesticated plants and animals, formed new social bonds, and built monuments to the heavens that had once betrayed them. Theirs is the ultimate testament to human resilience, a slow, stubborn rekindling of the flame of culture from the faintest embers. Every city, every field, every story we have today can trace a lineage back to those determined few who refused to let the story end. This resilience is woven into our very species. Yet, the very same evidence underscores our profound fragility. For all our intelligence and adaptability, we remain at the mercy of forces that dwarf our greatest achievements. A single rock from space, a climatic chain reaction we did not cause, brought a widespread and sophisticated way of life to an abrupt halt. It was a reminder that our place on this planet is not guaranteed, but contingent on a stable and forgiving environment. This balance defines the human condition. We build magnificent towers of culture, but those towers stand on a foundation that can be shaken by the cosmos itself. In our modern, hyper-connected world, this lesson takes on a new and urgent dimension. We have built a global civilization of incredible complexity and interdependence, a web of supply chains, digital networks, and concentrated populations. This system grants us unprecedented comfort and capability, but it also creates new, systemic vulnerabilities. A similar global catastrophe today would not merely disrupt hunting grounds, it could collapse the intricate systems that provide food, water, energy, and medicine to billions. The study of this ancient event, therefore, is far more than an academic puzzle. It is a crucial exercise in risk assessment and long-term preparedness. It humbles any illusion of total technological mastery, reminding us that our history has always been shaped by a tense dialogue between human ingenuity and uncontrollable external shocks. To understand the comet is to hold a mirror to ourselves, seeing both the unyielding strength that allows us to rebuild from ruins and the sobering vulnerability that makes such rebuilding necessary. This ancient drama of collapse and renewal is not just our past, it is a permanent feature of the human story, echoing forward into an uncertain future. Our ancient story demands a modern response. The evidence for a comet impact is not just a window into our past, it is a blueprint for our future. If such an event could reset the world once, the possibility, however remote, exists for it to happen again. This is not a call for fear, but for vigilance and intelligent action. Around the globe, a quiet but determined effort is underway, a field known as planetary defense. International space agencies, led by efforts from NASA and the European Space Agency, are systematically scanning the skies, cataloging every near-Earth object larger than a city block. Their goal is to find them decades, even centuries, before any potential threat materializes. This is a monumental census of our cosmic neighborhood. But finding an object is only the first step. The next is learning how to move it. In September 2022, humanity took its first practical step in this direction. NASA's DART mission, the Double Asteroid Redirection Test, was a spacecraft deliberately aimed at a small moonlet orbiting a distant asteroid. The impact successfully altered the moonlet's orbit, proving that we can, in principle, use kinetic force to nudge a threatening object off a collision course with Earth. It was a historic demonstration, a proof of concept that planetary defense is not science fiction, but a feasible branch of engineering. The lessons of the Younger Dryas make this work profoundly urgent. They tell us that existential threats from space are not theoretical nightmares. They are documented chapters in Earth's own biography. Investing in the telescopes, the missions, and the international cooperation required for planetary defense is perhaps the ultimate investment in the long-term survival of human civilization. It is a practical application of learning from history, of using our knowledge of a past catastrophe to safeguard all our tomorrows. Beyond the telescopes and deflection technologies, this knowledge fosters something deeper, a cosmic awareness. For centuries, we have viewed ourselves as separate from the cosmos, living on a stable stage under a distant backdrop of stars. The impact hypothesis shatters that illusion. It places humanity firmly within a dynamic and sometimes hazardous solar system. We are participants in a cosmic environment, subject to its beautiful rhythms and its rare but real dangers. This awareness is humbling, but it is also unifying. The threat from above recognizes no borders, no nations, no ideologies. It is a challenge that can only be met by a united human family, applying our collective intelligence and resolve. By understanding our past encounters with the cosmos, we gain the perspective needed to responsibly steward our future. We ensure that the next reset event, should one ever approach, is not a cataclysm we merely endure, but a challenge we see coming, a problem we have prepared for, and a danger we can collectively choose to prevent. From microscopic diamonds to massive craters, the evidence converges into a single, breathtaking narrative. We have traced the echoes of a day when the sky fell, a cosmic event that did not just change the weather, but rewrote the entire human story. The geological fingerprints are clear, a global layer of ash and soot, a rain of platinum dust, and the silent scar of a crater under the ice. The biological record speaks of sudden, sweeping loss as great beasts vanished and human cultures faced an unimaginable bottleneck. The climatic data shows a planet thrown violently back into a deep freeze for over 1,000 years. And woven through it all are the human echoes, the myths of fire and flood, and the mysterious monuments built by survivors in the dawn of a new, uncertain age. This is not a story of slow, steady progress. It is a story of shattering disruption and resilient rebirth. The comet's arrival may have erased one world, but in the long, cold shadow that followed, the seeds of our modern civilization were planted. The desperate innovation of agriculture, the complex social bonds needed to build places like Göbekli Tepe, the very turn from nomadic life to settled society, all may have been accelerated by that ancient crisis. Our past is not a straight line, but a cycle of collapse and renewal, a testament to both our profound fragility and our incredible tenacity. The great scientist Carl Sagan once observed that extinction is the rule and survival is the exception. Our species is that exception, a thread of memory and ingenuity that persisted through a cosmic winter. This exploration is more than a historical puzzle, it is a mirror. It reminds us that our civilization, for all its towers and technology, exists within a dynamic and sometimes unforgiving cosmos. It challenges us to look at our own place in time with both humility and wonder. How does this deep past shape your view of human history? Does the idea of a civilization reset alter your understanding of our resilience? If this journey into one of history's greatest mysteries captivated you, consider subscribing for more explorations into the unknown. We would love to hear your perspective on this civilization-altering event in the comments below.